Thank you for your introduction. Today, my approach is different from basically from others. This is a kind of semi-empirical method to introduce correction factor to better represent theoretical amplification. The outline of my presentation is something like here. We first derived the site amplification factors here called SAF from the Japanese nationwide networks by using the so-called generalized inversion technique here after GIT. And we can use these SAFs from strong motion prediction for strong motion prediction at this target site. However, we need at least observed weak motion or microtremors to get site amplification factors. We tested the capability of the current velocity models in Japan produced by NEED, whether they can reproduce or not the observed SAFs by 1D theoretical transfer function, here TTF. We found that the calculated TTF show more or less acceptable goodness of fit with the observed SAFs at about 1/2 of the site. However, they tend to underestimate the SAF in general. Therefore, we propose here a simple empirical method to fill the gap between the observed SAFs and the theoretical transfer function. First, I would like to explain briefly how we get the generalized spectral inversion. Here, the Fij is a Fourier spectrum for the earthquake I at the site J in the frequency range 0.12 Hz to 20 Hz as root mean square values of two components. And Si is the source term, and these are the path terms, and the Gj is a side term. Here, Gj is corresponding to the SAF. And our important point is that we use the reference site as YMG H01 after the extraction of the site effect there. Although this site has a rock outcrop with a shear velocity higher than 1 km/s. So our site effect is site effect relative to the seismological bedrock. Also, our analysis here is focused on the S-wave portion with relatively short duration. We divide Japan into 6 regions with different path terms, and we use earthquakes with JM magnitude larger than 4.5, source distance less than 200 kilometers, focal depth less than 60 kilometers, and observation point at least 3. And in total, we have about 2,600 sites and 1,700 events. And in terms of the earthquake site pairs, it is 150,000. And the result of the source pattern site looks nice, as evidenced by source spectra here, 1995 Kobe source spectra, as seen with the nice correspondence with the omega squared type. And also we see a very systematic frequency dependence of Q and site effect with the correspondence at some selected site, as I mentioned, with theory. And recent studies by Senna and Wakana constructed both the unified structure, both the deep and shallow velocity based on the various methods, including but not limited to the microtremor array measurement and SPT boring data, as well as the reflection and reflection surveys in a large scale. And this is a depth contour of the shear wave velocity 3.1 km/s or higher, And this is a depth contour of the engineering bedrock down to the shear wave velocity layer with 350 meters per second or higher in Tokai region. We have only both the Tokai and Kanto region so far. But when we calculate 1D site amplification factor, we found the SIG line here is the SAF from GIT, and dotted line is the 1D S-wave theory from the seismological bedrock to the surface. And as I mentioned, the matching is quite good at about 1/3, and maybe acceptable for about a half, but in general, frequency is slightly different, as well as the amplitude is slightly different, not perfect match. So we found that observed horizontal site amplification factor is much smoother than vertical site amplification factor after the fundamental peak frequency, and there is an underestimation of the theory in frequency range higher than the first fundamental peak. So in step 1, at 546 stations in Kanto and Tokai, we obtained modification ratio in frequency and amplitude. First, we calculate GIT empirical site amplification factor, as I mentioned, and also we calculate the theoretical 1D transfer function, and then to fill the gap between them, we determine as a grid search the frequency modification factor to shift the frequency in the right position, and also to match the amplitude, we introduce amplitude modification factor. And this is 4 examples of the modification. The original theoretical transfer function in dotted line is modified into red line that match to the observed site amplification factor. This is an improvement of correlation before and after with the correction with frequency modification factor. We use when correlation before the modification is higher than 0.6, then we restrict the searching range of FMR either 0.8 or higher and below 1.25 to avoid the unnecessary strong modification. Because if we shift largely, then we are going to match the next peak frequency, even though the matching is more or less okay. So here the limited sites with searching range, and these are the sites with lower correlations and get higher values. So this is a comparison between correlations between observed site amplification factor and the theoretical transfer functions at 546 sites, and all sites shows improvement, and those sites with negative correlation shows most of them high correlation without negative values. So this is a comparison between residuals. Residual is the average ratio between observed SAF and the calculated transfer function. So the good side was increased considerably to get about 80% are successfully good. And for the correlation, we also see a significant improvement from the original correlation to the modification with a value of 85%. The next step is to interpolate these FMR and AMR at 546 sites We use two-step interpolation scheme to get these values at every 250 meters grid, because we have a theoretical resolution of 250 meters grid in Senna's model. So we use first GIT interpolation scheme, GMT interpolation scheme by Smith and Wessel. It is called the surface function in GMT. And then next step, we use Shepherd function proposed by Lenka to get the 250 meters grid. And this is interpolated FMR and AMR. This is FMR and this is AMR. We see stronger correction of FMR in Tokai region is necessary in comparison to Kanto region, while larger AMR correction in Kanto basin is necessary in comparison to the Tokai area. However, we didn't see spatial correlation with geophysical parameters of the site, like VS30 or Z3.1, because they are already reflected in the transfer function. So this is a systematic distribution of our error in constructing the velocity model from the seismological bedrock to the surface. So this is a verification exercise, a validation exercise of this proposed interpolation scheme at these 4 sites. Before this interpolation, we extract these 4 sites data from the database and do the interpolation and compare the site amplification factor based on the interpolated FMR and AMR. Of course, the matching from the original AMR and FMR is better than this. Still, the correction makes site amplification factor similar to the observed site amplification factor. From now on, I'm switching to the growth aspect of the site amplification factor throughout the whole Japan island. In the same way, we can see the whole Japan response, island response, by using the observed horizontal site amplification factor. As I interpolated the map by GMT. And this is an animation starting from, 0.122 Hertz to 3 Hertz. And we see a systematic emergence of the basin like Kanto, Nobi, Osaka, Kumamoto, Sapporo, and Sendai. But it is also quite systematic to see amplification in high frequency in eastern part of Japan, much higher than the western part of Japan. And we can see high frequency amplification from 3 Hertz to 6 Hertz here. And we found also very spatially coherent characteristics, even in this kind of high frequency range. And once it becomes higher, then the higher amplitude region remain high. This is quite different from the theoretical prediction in for Japan. This is again 1D theoretical transfer function based on the whole Japan deep sedimentary basin structure, in addition to with the PS logging data of the Kenneth and Kickness side. And we see that when we use the theoretical transfer function, we see quite large deficient amplification, as well as the systematic fluctuation from frequency to frequency. That's a big difference, as we already seen in Kanto and Tokai region, so that we also need that kind of FMR AMR correction. However, we haven't done yet for the whole Japan. And as a gross aspect of the site amplification factor, we see, I would like to emphasize that the correlation of the site amplification factor we obtain from the seismological bedrock to the surface is quite consistent with depths down to the seismological bedrock, which is determined by need for whole Japan as a JCC structure. And we see this rock surface region in Kanto, but on average, Kanto's side, eastern side of Japan island is much deeper in terms of the seismological bedrock compared to the western side of Japan. That is reflected in the site amplification factor. So not only the long period ground motion, but also the short period ground motion is associated with the depths down to the seismological bedrock. So in conclusion, we found that theoretical transfer function from the vast velocity structure from the seismological bedrock to the surface is still not perfect to reproduce observed horizontal SAF. So we propose a scheme to first find a kind of mapping function represented by FMR and AMR, and then interpolate them to modify the transfer function. And even though individual site amplification factors show strong frequency dependence, the spatial variability of these frequency fluctuations are remarkably stable. Therefore, we may interpolate horizontal site amplification factor directly. Since the theoretical transfer function is deficient, so when we construct a beta velocity model, it should be really good. Otherwise, it would be better to use empirical site amplification factor. And our site amplification factor of stability of our site amplification factor comes from the fact that we use the seismological bedrock as a reference, and we use the relatively short duration of the ground motion. So broadband site amplification factor is a consequence of the upgoing and downgoing S-wave propagation within the basin, so that the separation of the influential frequency of the target of simulation and the corresponding depths is simply not possible. So this means that the seismic wave doesn't see the engineering bedrock. And the final note is that do we really need high frequency or not? We have been investing a lot to expand our knowledge to reproduce a high frequency component. And this is because engineers believe that the resonance is taking place to collapse the building. But our history of devastating structural damage shows the cause of heavy damage is not associated with the resonance in the elastic regime, but the input energy makes nonlinear deformation beyond the limit. So if we primarily concerned about the devastating damage of the structures, we need to take care we don't need to take care too much about the high frequency component, but we have to focus on the frequency range around 1 Hertz. That's my message. Thank you for your attention.
Great, thank you.